participants. Can you please confirm if you can see the slides on the screen? All right, good, thank you. So let's continue with the second part of the lithography process. So we discussed last time about the alignment, about the resist thickness, about the coverage, about the conformality in on some areas that already have features. Okay, for example, like this, where it's more challenging for the PR to cover if you compare to planar surface. Okay, so this will be among the issues that you'll face when you handle a lithography process. So there are many more, and there are many issues that are still unsolved in the fab. So like I said last time, some problems have been there for say if the fab was built in 2000, for example. So some problems will probably uh, have been present for about 15 years unsolved. Okay, tak semua isu yang kita dapat solve dalam fab. So normally when you join with a fab, then when you have issues, when you have problems, then they not normally call the problems as issues. Okay, banyak issue. Issue means problems that you have to solve, and there are many problems that suddenly go away as well. Suddenly go away unsolved, not understood at all, or not understood completely. Then probably the problem go off for 1-2 weeks or perhaps 1-2 months, and then the third month suddenly the problems come back and still trying to be understood. Okay, so that's mestinya semua problem yang you ada dalam industry you can solve, even though you play with the problem, you are on the problem, you're trying to solve the problem day in, day out. There are still things that are not understood by even senior engineers, staff engineers, managers, directors. Okay, so it's been, the problems have been puzzling the whole team for years. Okay, so when you talk about effect of resist thickness, there'll be issues where if you have thickness variation on the wafer, in particular, if you have a coverage problem, just like what I showed on the previous slide. So that will result in non-uniform exposure during the exposure step. So let's recall the CED step. So when you exposed the light of a specific wavelength to the whole photoresist on the wafer, so some areas will not be exposed uniformly due to variation of thickness. Okay, so the resist can be underexposed when it's thicker and overexposed when it's thinner. So let's recall the DOF. So when you understand the DOF, or the depth of focus, so we can only ensure that the resolution, the contrast, okay, the contrast of the features is only ensured within the DOF. So dalam window tu je, we can be sure of that the resolution of the photoresist or the features that we're going to develop will be good, okay, in spec. Whereas if you have outside the DOF, the focus cannot be ensured, the quality cannot be ensured, the contrast cannot be ensured as well. So you'll probably have less sharp images or less sharp features developed if you are out of the DOF, the depth of focus. So this can lead to line width variation. Okay, line width variation, that means when you want to, so let me just sketch here. You have a silicon on, say let's just put the resist on. Normally you have oxide under the resist. So when you want to print lines, remember we can print either lines or holes. Okay, when you want to print lines, for example, so that means if you have this problem of non-uniformity, you probably have a comparable CD on the side. Kiri kanan CD dia sama, line width sama. CD means line width. Line width here equals CD. This. Recall DICD, okay, develop inspection CD. So maybe CD in the middle is slightly wider. So this is what it means, line with variations. So if you have, if you look at the top view of the wafer, tadi tepi ya cross section. If you look at the top view, if you're measuring your CD kita measure pakai SEM, SEM, scanning electron microscope to measure the CD. So say you have like thousands of dies, for example. Saya tunjuk yang sikit ya, just for illustration. So just say this is your one die or one chip. Dalam chip ni, if you zoom into the chip, then you're going to have like billions of transistors. And say if you exaggerate the feature size, then you'll probably see this cross section. Saya exaggerate je, so maybe you can see 3 lines. Dua kat tepi, satu kat tengah. Actually ada billions of lines. So exaggerate just to illustrate the case. Okay, so bila you measure, then you'll probably see it could be in different trends. Mungkin some issues you can only see wider CD in the middle and then narrower CD on the sides. Or maybe if we relate to the case where we have problem with hot plate last time, it's going to be skewed. Mungkin out of the whole wafer, then this whole side has high CD and perhaps the other 50% has lower CD. Okay, the problem tu boleh jadi banyak dalam bentuk. It can be like half slanted problem. It can be center CD low but sides okay, but maybe center CD high but sides okay. So the issues can come in many different forms. Okay, dia tak semestinya satu issue je on CD. It can be all low or all high or 50% low or 50% high, or there's maybe there's no trend at all, or maybe in the center of the chip it's always high, on the side of the chip it's always low, or there is no trend within the chip but you can see some trends on other chips. So dia boleh jadi thousand of different symptoms. So itu yang sometimes is puzzling bila you work in the industry. Sometimes some problems are still unsolved because they just don't show any systematic symptoms. Okay, systematic means ini knowledge untuk you guna as your bila you kerja ni or as an intern later on. Systematic means it shows repeated trend. So bila you masuk industri, orang akan cakap engineer lah normally technical team akan cakap systematic issue or random issue. Systematic means it shows some trend to some extent. Either it's 100% trend or 70% trend, but 30% there's no trend, or completely scattered, random. There's no trend at all that you can see, you can observe from the results. Okay, so systematic or random. Kalau you present as an intern later on, an engineer later, kalau you wafer fab lah, I don't know about backend, so I think it should be the same. Then your boss will probably ask you, is it systematic or random? So that's what it means. Okay, let me know kalau your boss tanya soalan ni. So at least you know now that if it's systematic, then your boss is expecting some trends from the results. Okay, maksudnya issue tu ada tunjuk satu trend, either it's 50% slanted ataupun always center CD high, always side CD low, or there's no trend at all. Okay, so systematic versus random. So this is a good knowledge for you to learn. So light intensity varies with depth below the surface due to absorption. So this is an expression or equation that we use because we learned this one last time during 386. light intensity varies with the depth below the surface due to absorption, right? Intensity at any position, Ix, any distance into the surface, resist or silicon or whatever, so equals to I naught. I naught is the peak intensity at the surface, so exponential negative absorption coefficient times the distance. Okay, so you can recall this while we were discussing about light absorption in semiconductor material in 386. So where alpha is the optical absorption coefficient of materials. Okay, so when you talk about lithography, so it revolves around optics, it revolves around light material interaction. So anything that you learn that are related to light material interaction, so the courses, the content will be applicable to this particular area. So a process called bleaching, in which the exposed material becomes almost transparent, that is alpha decreases at the exposure, happens as well. So therefore, more light goes deeper to deeper layers after bleaching near the surface of the PR. So if there are some conditions where alpha decreases after exposure in the resist, so that is called resist bleaching. The transparent. I must say, when the resist is transparent, what does it mean? So let's recall what we learned in 386. When the resist is transparent to the incident light, what do you expect to happen in the resist, or in the reaction, or in the mechanism that's supposed to happen? Becomes almost transparent. Anyone? Let's recall your previous knowledge and then couple with the mechanism that we learned in lithography relating to the resist. Anyone? Go on. If the resist becomes almost transparent, that means, okay, siapa-siapa ni? Haziq. Okay, Haziq cakap, what is this? No reaction. Okay, he said no reaction. Why no reaction, Haziq? Kenapa tak ada reaction dengan resist?
Sebab sebab photoresist tu tak dapat dia tak absorb light UV tu. So no reaction.
Right, okay. Thank you. Amirul, light can pass through. Right, so sama macam jawapan Haziq. Any other answers? Light can pass through. Bila light can pass through, what do you expect to happen in the resist? Anyone else? Juaria, what do you expect to happen? Sama, okay. Any other? Huda, Huda? What do you think? Any answer, Huda? No answer? So yeah, okay, right. So yes, when the resist becomes transparent, so the incident light just pass through the resist without any reaction. Okay, maksud tak ada intended reaction lah within the resist, and well, there's no reaction. So if you develop the resist, then you won't see anything happen. So there's no hardening, there's no solubility. Resist tu macam you coat je lah, as coated, that's it, right? Okay, some common process issues. There are thousands of different process issues in lithography. So these are only some of the issues. Tapi ini sebenarnya banyak isu. I cannot describe everything. So spin defects, for example, if you talk about spinning defects, so related to coating or development, whatever yang involves spinning, coating, developing. So there could be pinholes, right? That could cause contamination. You can probably see air bubbles in the resist. Kita dah discuss last time. Some can be spotted at VI, visual inspection. Some cannot be spotted, perhaps because they are just too small. Cloudy film due to excess of moisture. So normally in the lithography equipment, the temperature, the humidity need to be controlled very well. Okay, when you have the excess moisture, then this you will expect some reaction on the wafer, on the resist. Uneven coating due to misaligned nozzle, due to inadequate photoresist ataupun tiba-tiba resist dispense ada interruption. Say if you're supposed to dispense 1 ml, for example, before the spinning, so tapi mungkin you just dispense 0.7, 0.8, then you'll probably see a streak of resist. So if volume that cukup, but then you spread at the same speed, then you will see some areas, especially the edges, will not be covered by resist. And you can tell because normally it will be very, very obvious. Uneven coating, okay, too thick or too thin, cause due to wrong spin speed, resist viscosity, due to aging sometimes, if the resist expired. That's why you have to do PM. PM too, you have to check, technicians, equipment technician will check the shelf life of the resist every single time. Okay, kena check, tengok dah expired belum. Kalau expired ganti, tak expired, leave it there, right? So aging will be the issue, especially if the loading, the order daripada customer tak banyak. Bila order tak banyak, you run the resist less, so therefore tak habis lah, macam tak habis guna. Or humidity changes perhaps, or fluctuation, comet defects, okay, bubble or particle during dispense, okay. Critical dimension issue, okay, perhaps you can relate this to the LER, that is in the assignment 1, okay, line edge roughness. So CD related issue, the measured CD or the printed features of the developed or the final CD after etch. So recall DICD versus FICD. So DICD is developed inspection CD, or in this case after developed, or FICD, final inspection CD, which is after etch. We're gonna cover in etching later on as well. But note that there'll be 2 points where you measure the CD, DI and FI, after litho, after etch. You'll see why is it the case. It can be line width or spaces. So recall that we can either print metal lines, or sorry, not metal lines. We can either print lines or holes. Okay. So typical error tolerance is 10%. This one depends on your SPC chart. Okay. For example, in this case, if you look at these features, 2D, dari atas ni, you can see that the CD is 0.1 micron in width, ataupun 100 nanometer lah. So if you see these features from the cross section, then you will see something like this, and that square shape. So that will be the profile. Then this one will be nothing. That will be the profile. Nothing. Profile, nothing, like that, right? This cross section, cross SEM, cross section lah, X SEM. Yang atas top view, bawah cross section. So that's how it looks like. Kalau hole, then if you see hole, then like that, then the cross section will be like that. Okay, that's how it goes. CDs are directly related to exposure dose. Okay, CD is related to exposure dose. How? Okay, if you're talking about lines printing, macam ni, line. If you're printing lines, macam ni, not holes, lines. If your CD is too large, for example, your target is 0.1 micron, 100 nanometer is your target. Somewhere. Suddenly, when you measure your CD on SEM, and you measured 125 nanometer, your intended is 100 nanometer, and perhaps plus minus 5. So that means you can only swing from 95 to 105, but you measured 125, so that means the CD is already out of spec. Dia dah keluar daripada window. So your target is 100 plus minus 5, so that means it can only swing within 95 to 105. So you cannot go below 95, you cannot go above 105. So now you measure on 125. So in this case, if it's due to the exposure dose in the scanner, so that means when you have your CD too large, so the root cause could be the dose is too small. Okay? For example, if you're supposed to run at 20 millijoule, for example, DUV, yeah? 20 millijoule per second squared, maybe due to some reason or some fluctuation in the exposure system, maybe instead of exposing the wafer at 20 millijoule per second squared, maybe the system is only exposing the wafer at 16.5 millijoule per second squared, and that results in 125 nanometer of CD. Okay, so for lines printing, the dose and the CD is reciprocal to each other. So if the dose is too high, your CD will be too small. If your dose is too small, then your CD will be too high for lines. On the other hand, for holes, so the CD and dose relationship will be proportional. If your dose is too high, your hole will be bigger. You can diameter of CD of hole kat sini still the diameter, but then it's hole. If your dose is too high, then your CD will be high. So that means your hole diameter will be higher, bigger. If your CD is too low, then your hole will be smaller in diameter. Okay, yeah. For hole, the CD and dose relationship will be proportional. For lines, CD and dose relationship will be reciprocal. Okay. Right, let's have a look. If for CD issue, if you have a good CD, then this is what you get, right? So that's what is intended and that's what you obtain. On the other hand, if you have a CD loss, that may happen to throughout the lines, dia boleh jadi the whole loss maknanya semua jadi lagi kecil, narrow. Or maybe you just have some loss in between, in the center. So that's why I said the problem can come in many different phases. Dia boleh loss kat tengah, dia boleh loss kat tepi, dia boleh loss semua, ataupun dia boleh okay je, right? So as a process engineer, ni process engineer punya job, this is part of the thing that you have to do. Process engineer, they have to sustain the process performance in mass production. So kalau ada issue, then you have to check what goes wrong and why is it so. How do I correct the problem and how do I prevent the problem? Okay, bila ada issue dalam line, so this is what you have to think from now. I want to instill from now. What is the problem? That means you're identifying the problem. What could be the root cause? So you need to troubleshoot, to drill down to the root cause. The moment you know the root cause, or root causes, perhaps more than one, you then have to correct the issue. So you get the CD back on track. So if the CD was like 125 and you can only sustain the CD within 100 plus minus 5, so you have to get back the CD on track. Okay, so if you talk about scanner energy dose, katalah you punya CD tadi tu you measure 125 and your spec is 100 nanometer, and the root cause that you found is due to the exposure dose drifting, and then you're supposed to expose at energy X, but you're actually exposing at Y. So if you got 125, so what do you want to do on the exposure dose? If you're printing lines, anyone? You're supposed to get 100 plus minus 5, and you're getting 125, and the root cause is exposure dose drifting, and you're printing lines. What are you supposed to do as a process engineer in this case? Saya bagi soalan real life terus. So what would you do? To the exposure dose, you're exposing at, say, 25 millijoule per centimeter squared. What do you want to do next? Anyone? Any process engineer here? Lithography? Or potential process engineer for lithography? Okay, what would you do? Come on, you can write in the chat box and you can unmute yourself as well. Let's just discuss and see. What would you do? Saya nak ajar you troubleshooting mindset while learning the contents. Mimi, what would you do, Mimi? You are the PIC, you are the person in charge. You are the engineer in charge for this particular layer to print lines, and your CD is drifting on higher side. What do you want to do on exposure dose? Hear me? Hear me? Are you here? Still thinking. All right. So assume this is our operation meeting. Operation meeting. You're updating to your CEO. Okay. So Amiro is the backup process engineer for this line. Okay. You're printing lines, and your CD is drifting on the high side. You're supposed to get 100 nanometer, and you're now getting 125 nanometer. You're printing lines, and your problem is due to the scanner dose. What do you want to do? Amiro said, kurangkan dose, reduce the dose. Okay? Are you sure, Amiro? Why do you want to reduce the dose? Boleh unmute yourself.
Because the CD is too small.
Too small or too high? Are you getting too small or too high now? What is your target CD now?
Oh, CD is too big lah.
Okay. So identifying the problem first. So what is the issue now? The
so
CD is?
we need to increase the dose.
Okay. Why do you want to increase the dose? I want to teach you the troubleshooting mindset now. Why? Okay, you're proposing to increase the dose, right? Why? Bila you cakap dalam operation meeting, the next question will be why. The next question after why will be how much. Okay, anyone would like to back up Amirul? This is our operation meeting now.
Apa dia punya question, sir? Doktor?
Okay, your target CD is 100 nanometer. Your printing lines as on this page. Your target CD is 100 nanometer, and you are getting 125 nanometer from your SEM measurement. So, and the root cause has been identified, which is due to scanner dose drifting. Maknanya dia tak stay on track lah. What do you want to do next? To get the CD back on track into the SPC chart.
Oh. Kalau nak support Mirul, Mirul cakap tadi kita kena decreasekan
Dia cakap increase.
Oh, increase. Increasekan.
Are you supporting him or against him?
Tapi kalau kita increasekan exposure, bukan sepatutnya lagi banyak yang akan CD akan kurang sebab dia overexposure.
Okay, so your CD will?
So CD makin decrease.
Okay, so will you get back on track?
No.
Why not?
Because of overexposure on photoresist.
Yeah, but you want to increase the dose, right?
Okay.
So will your CD reduce?
Kalau kita increase dose, yes.
Okay, Amirul, yes, you want to add?
Kalau kita increase dose, CD dia makin kecil lah. Jadi daripada 125 tu dia akan jadi 100.
Okay, all right. Any other? Okay, thank you. Any different answers? Anyone object this answer or this approach? Faris, what do you think? Saya ajar you ni real case operation meeting macam ni ataupun department meeting lah at least lithography. So kalau you masuk fab ni, katalah join intern lithography pula, for example, then you will appreciate this. Exactly, 100% sama. This is the question we had last time and daily. Okay, anyone else? Any objection? Any different approaches would you like to propose? Faris, what do you think? Tak ada jawab ha dalam department meeting nanti buah gelak je. Bukan buah gelak lah, buah marah. Kavina, what would you do? You are the person, you are the engineer in charge of this layer. You're supposed to get 100 nanometer, you're getting 125, you're printing lines, you're suspecting the energy dose to drift. Still figuring out, okay? Anyone else? Mac, lama tak ada suara Mac. What would you do? Mac? Mac cuti hari ni ke? Kita dalam department meeting Sakinah, you are the next person in charge of this layer. What would you do? Dalam department meeting every single day, department meeting ni every single day tau. It's not like once a week. It's every day 8 to 9. Kalau Sitiara lah, other companies I'm not sure. Still thinking, right? Think first, I'll come back to you, okay? Kavina and Sakinah. Right? I'll come back to you shortly. Let me tell you stories first. I'll come back to you while you're making your decision. So it's everyday kind of meeting, 8 to 9, department meeting. 9 a.m. Sunday operation meeting. Manager masuk dengan director, blah, blah, blah. Bigger meeting. Bawa result dari bawah. Status dari bawah masuk ke operation. Then kalau tak ada big issue, then okay. Kalau ada big issue, then maybe next level. Okay. So in your everyday department meeting, you'll be asked about this. If you're the person in charge of this particular layer, say you're printing polysilicon layer, engineer will be in charge of layers. Photolithography, and you're talking about front end and back end. So front end, maybe you're in charge of implant and polysilicon yang awal-awal proses untuk MOSFET. If you're in charge of back end dalam litho, then you're in charge of metal 1, metal 2, VR1, VR2. We're gonna see that when we learn about interconnects, right? Metal 1 sampai metal 3 here, metal 4 sampai top metal. So there'll be 1 or 2 or 3 engineers in charge. So anything happens to the particular layers within your portfolio, you have to be answerable every day. Okay, kalau tak ada issue and everything is stable, then okay. Kalau tak stable, then you have to be answerable. Okay, I'll come back to Kavina before Sakinah. Okay, Kavina, what would you do now? Your CD is drifting on the higher side. The printing lines is supposed to get 100 nanometer, you're getting 125. You're suspecting your energy dose to be drifting in the scanner. The solution is reduce the dose. Maybe, okay, kenapa nak reduce the dose? Your printing lines, your CD is drifting on the higher side. Out of spec on higher side. Your printing lines. Any argument, any justification why? Sakina? Inspect DOF. Before DOF, let's dive in that. This is very straightforward. It has nothing to do with DOF yet. Kalau masuk DOF lagi complicated. Then you have to verify the whole thing. This is just CD on target or not, and in relation to the printing lines or holes. Sakina? Reduce dose. Okay. Reduce dose to make CD large. Okay, now let me ask you, what is the problem now? What is the issue now? Can you identify the problem? Anyone? Amiro, can you repeat the problem? Juara, CD is large. Amiro, can you repeat the problem statement?
The problem statement is that we have one CD of 125 nanometer.
Yes.
So
Yes.
we want to reduce it to the target 100 nanometer.
Okay. Then?
So what we do is we increase the dose as for to get the CD become smaller.
Okay, so that when you get it to be smaller, then
and then we get from 125 nanometer we get to 100 nanometer CD.
Okay, is that clear? Or so bila you nak troubleshoot problem, it starts with problem identification. Saya nak ajar sekali ya, one go saya ajar semua benda. So it starts with problem identification. You have to be clear of what is the problem before you do anything, before you start your thinking, before you consider the potential solution. What is the problem? The boss akan tanya dulu, what is the problem now? CD is too high. Why is it too high? I suspect energy dose drifting. Why is it drifting? Then you have to go back to the 5 whys analysis that I taught you last week, I think. Okay. So sekarang the issue is CD on the high side. Okay. Sekarang bila you nak identify the problem, you always have to go back to sketch. Okay. Physics without sketch is not physics. You kena sketch physics. So let's sekarang kita dah discuss last time about SPC chart kan, briefly lah. So this will be very important. I've tried to understand this before your internship interview. It's super crucial. Okay, your target is 100 nanometer. Pardon my sketch, huh? So, and your fluctuation is plus minus 5. That is considered okay within the spec. So you can only be here. So that means you're only okay between 95 to 105. And now your CD measured after the ICD is 125. Where is 125 on this chart?
Lagi tinggi.
Lagi tinggi lah kan? Simple, right? It's very simple, right? Dulu atas ni lah kan? Lagi tinggi guys tu. Okay, so our spec is called out of spec, OOS. Kalau tak jauh sangat out of control, ada level lah, OOC out of control, OOS out of spec. Okay, so now your CD has been drifting here, there. Dah lama dah, contohlah 3 jam dah kat sini. Baru nak sedar. So then you're printing lines. Okay. If you go back to the previous slide, okay, you dah ada guideline kat sini kan? Saya dah bagi guideline. If your CD, okay, kita dah belajar tadi, untuk line, the dose and CD punya relationship is reciprocal. So that means if your CD is too large, that means the dose is too small. So the problem is dose is too small. So to be able to get the CD, okay, you come back to here. Kalau you nak dia punya relationship is dose is proportional to 1 over CD, or dose and CD is reciprocal. Okay, for lines, kalau whole, then proportional. In line, just we're talking about lines now. So to be able to reduce the CD, nak turun balik ke sini, you have to develop more, right? Isn't it? Sekarang ni CD besar. Bila CD besar maksudnya apa? Bila you measure from the cross section, you want to get something like this. This is what you have to get, but you are getting this. It's very wide, right? 125. You're supposed to get 100. So that means your exposure dose is not enough to wash, to remove, to induce photosolubilization in the positive resist, in this case, to 100 nanometer. Maknanya kita patutnya remove lagi ni. Tapi dose tak cukup. Dose tak cukup. So you have to then increase the dose because the relationship is proportional, is reciprocal. Increase the dose so that your CD will reduce. Bila your CD will reduce, macam Amir cakap, you will reduce the CD from 125 heading downwards lah. Then we're targeting to 200 nanometer. So it's a matter of how much is the dosage. Then nak kena tengok balik lah dose to CD punya magnitude and all the stuff, which is more detailed. Tapi at least for now, the direction is to be able to go lower on the CD. You have to increase the dose in order to wash more, in order to remove more of the resist so that you end up with 100 nanometer as intended. So my point here is, bila you nak buat troubleshooting, in any cases, tak semestinya kerja kat fab ya. Bila kerja as engineer atau as technical person dalam career later on, first is, before you decide on anything, define the problem clearly. Understand the problem clearly. sketch the problem, draw SPC chart, tulis relationship, draw the cross section. Lepas you nampak SPC chart, nampak relationship kat sini, then you sketch the CD problem. I supposed to get this, but I'm not getting this, but instead I'm getting this. By these sketches, at least, oh, okay, so this is the actual problem. So this is defining the problem to make sure that you are clearer. Okay? Bila you fikir ya, anything that is not written down is not clear enough. I think Mark Zuckerberg said this. Apa yang you ada dalam fikiran ni, selagi kita tak tulis, selagi tak lukis, it's not clear enough. Sebab anything that's not written, you just thinking. It's not written, it's not translated into sketches or handwriting in front of you. It's not clear enough. Okay? Bila you tulis, bila you sketch, oh, ni lah problem dia. Sebenarnya you dah fikir lah, tapi bila you fikir, they are there. Campur benda ni. It's vague, it's still vague. The moment you put on sketches on the paper, oh, this is the problem. Now you understand more. Padahal benda tu dalam dia punya idea sebenarnya. Ada kat sini. Tapi selagi you tak translate into this, you don't understand. Sekarang bila, oh, okay, this is the issue. So then, what do I do next? Okay, so it always starts with defining the problem, understanding the issue, defining the problem statement. Macam you buat thesis kan, FYP. Apa problem statement? Selalu you punya examiner akan tanya dalam Fiverr, what is your problem statement? Why do you do this? Why is it important? Problem statement, right? Defining the problem. Dan bila dah define the problem, you think of potential root causes. In this case, kita suspect CD drifting due to energy drifting in the scanner, and then potential solutions to correct the problem, to get the CD back on track, and then in the future, how do you prevent the problem from happening again? So this is pretty much the 8D skeleton yang saya dah summarize lah, from defining the problem identification sampai preventing the problem from happening in the future. Okay, so just embedded into this single slide, CD problem. Tapi sebenarnya ni baru CD problem, belum lagi defect problem, belum lagi focus drift, belum lagi thousand of different things. So can you see the point now? As far as CD issue is concerned, and how do we do troubleshooting? How do you start the thinking process? Okay, bila nak jadi engineer atau any technical person, dia kat sini dulu sebelum you pergi ke solving problem and solve big problem, breakthrough, whatever, sini dulu. Right? You have to start with thinking first. You have to be clear what is the issue first. Kalau you just imagine kalau you define the problem wrongly, macam tadi kita discuss kan, kita still learn to define the problem. Kalau you tak clear on problem, CD ni high ke low sebenarnya? So aku nak apa sebenarnya? Nak bagi low ke nak bagi high? So apa relationship dia dose dengan CD ni? If that stage is already vague and not clearly defined, just imagine what's going to happen next step. You akan, in this case, you'll probably reduce the dose. Then what happens to the CD? Instead of 125, next batch you measure 135. So apa you reduce the dose? Right, you are going into the wrong direction, opposite direction. But at least this discussion, I'm trying to instill the thinking, the mindset, the process, the troubleshooting. Really, you have to define clear first. So the rest more comes later. Problem identification comes first. If you get that wrong, your very first step is wrong, then forget about the rest. Tak payah tunjuk data, tak payah tunjuk conclusion. It's a waste of time. So that's what you'll get in the operation meeting. Kalau department meeting, kalau your problem definition is wrong, your managers, your director will just say in your face, they will be very straightforward. Okay, you don't have to show, stop it now. You go back and define the problem. That's it. Dia tak mahu tengok on data. Because tak kira you dah troubleshooting 3 hari ke, 2 hari tak tidur malam dalam fab ke. If your first page is wrong, okay, done, you go back to the fab, get data, and present tomorrow. As simple as that. Okay, it's very straightforward dalam operation punya apa tu presentation. Kadang-kadang you will see this. Okay, I bet you will come back and tell me, yeah, it's true. You will develop thicker skin when you join industry. Lepas tu kalau you dah join mana-mana, kalau you dah develop all this thick skin ni, then the rest will come easier. Right, so that's one. Saja nak illustrate to you ya. Almost 11. So let me just go for 5-10 minutes and we'll stop for 10 minutes. So another problem is misalignment. Okay, misalignment X, Y, theta. Okay, it can be like that. It can be X, it can be Y, depending on how you define X, Y. So it can be completely a mixture of a couple of axes, say X off, Y off, theta off, and something is really, really wrong with your exposure process. And still, you will drill down this issue just like what we discussed in the previous issue. So define the problem, then the moment it's clear, what are the potential root causes, identify the root cause, what are the potential approaches, solution to fix the root cause, corrective action, like kita panggil, get the problem, correct the issue, corrective action, and then how do you prevent the problem from happening in the future. So bila you troubleshoot, it's not only getting the problem to be solved, but you also have to be sure that it won't happen in the future. So bila you bagi, let me tell you this, my previous boss, bila you bagi preventive action, you propose preventive action that this problem will not happen in the future, you will probably get how confident are you it won't happen in the future. Are you 100% confident? 95% confident? 90% confident? 80% confident? 70% confidence? Or just more than 50% confident? And why? Okay, and then you will be really on your toes to explain. Kalau you're 100% confident, you say 100% confident that it won't happen in the future, then tiba-tiba minggu depan jadi balik problem ni, habis. Kena basuh lah. So yeah, you'll see this over time. Okay, saya bagi kat you the right mindset. I don't want you to be culture shock bila you join intern, you start kerja ni, oh nampak macam indah belaka. I'm not discouraging either, but I'm just telling you the whole story, the real story, so that bila masuk, okay, you expect this kind of culture to happen day in and day out, so that you are more prepared physically and this one as well, mentally. Okay, misalignment. So these are just among the other issues. Develop defects, for example. Let's have a look at this. So if you have perfect CD, your perfect CD will be something like that. Okay, katalah you nak measure kat sini. So the CD can be measured here in the space kat tempat kosong, you can measure CD as well, or you can measure CD in the line, dekat line itself. So it depends on the algorithm defined on SEM. Kalau you define to measure the space, then it will always find the space between features. Kalau you punya algorithm is defined to measure lines, then the SEM will always find the lines to be measured. And then whatever that is measured is reported on the SPC chart as inspect or drifting on the high side, drifting on the low side. So that will go back to the algorithm. Okay. So in this case, if you have overdeveloped problem, if you're measuring the space, that's why the keyword is very important. Tadi kita print hole ke line. Kalau line, then it's going to be proportional. Kalau hole is going to be proportional. Kalau line is going to be reciprocal. So in this case, if you look at the below left image, if you have overdeveloped issue, that means you don't remove extra than what you should, then you have overdeveloped issue. Okay, so if you're measuring the lines here, so that means you're expecting the CD to be smaller or bigger. If you overdevelop, you expect the CD to be bigger or smaller if you're measuring this lines. Katalah you ada line penuh lah kat sini. So do you expect the CD to be smaller or bigger if you overdevelop?
Expect CD tu lebih besar lah.
Kenapa lebih besar? You overdevelop, you are measuring lines. This line, this one. Saya tak cakap space, saya cakap line. That's why the keyword is very important. Kalau space kat sini, you measure space, kosong ni. Sekarang you measuring this, the green one. And you overdevelop, you expect the CD to be high or low?
Expect the CD to be higher.
Higher sebab?
Higher sebab CD tu kecil.
The algorithm
space
is
dia
measuring
besar.
lines. Okay, you are
Sebab
measuring lines. You are not measuring space. You are measuring lines. Kalau
sebab line
hijau
tu
ni.
kecil.
Bila line kecil, CD besar ke CD kecil?
CD kecil.
So your CD is lower or high? Higher or lower?
Lower.
Lower, right? Not higher,
Yeah.
right? So that's why it's very important to understand the keyword here. You're measuring lines and you overdevelop. So your algorithm measure line tau, bukan space. Kalau space kat tengah ni. Kalau space, then you overdevelop, you measure wider space, right? Tapi wider space at the same time means narrower lines. So that's why you have to know the algorithm. Nanti bila kalau jadi litho engineer lah. Kalau intern, I don't expect you to fully comprehend this. Tapi it's quite straightforward really. Kalau you faham ni, then you masuk intern lithography, then you won't have any problem to be absorbed as litho engineer. I bet you. Kalau ada vacancy lah, if you're good enough, understand all this basic, why waste time on somebody else, right? You are here. If I were your engineer in charge, yang monitor you, I'll just absorb. As simple as that. So understand, right? Overdeveloped or underdeveloped. Kalau you're underdeveloped on the right hand side, okay, underdeveloped means you don't remove enough resist. So more resist supposed to be soluble. You're not supposed to have this at all. You want to have something like that. And this, you want it to be very clear, clean cut, square shape. Ideally. But kalau you are left with this, underdeveloped, we call that coming. Resist coming is a form of defect that we have in lithography. Defect. Kita panggil dia defect. Tapi the detail is resist coming. Coming means it's not removed. Dia mungkin tiba-tiba you ada tumpuk kat sini. Some resist patches not removed. We call that coming as well. So due to something to be identified, we have coming on the wafers. Okay, we have resist coming. Not developed, not well exposed, or thickness not uniform, patchy here and there, or defects. So bila you identify the problem clearly, you don't have ada problem. Bila you nak go down to the potential root cause, tadi the real case like this. Bila you nak identify the root cause, bila you identify the problem, you will need to narrow down from say 20 or 30 potential problems to 1 or 2 that you want to identify clearly. Bila you dah decide on one particular problem, there are perhaps 10 or 20 different potential root causes that could lead to the problem yang you dah identify tadi. Maknanya, pun identify problem, dah dapat satu. Kemudian bawah problem ni ada 20 potential root cause pula. You kena narrow down pula to 1 or 2. So that's the work that you have to do later on. Process sustaining, process improvement, troubleshooting. Bila you tengok job description process engineer, these are the thing. You know, identify the root cause, kemudian yang mana satu root cause daripada 20 ni, what are the top 3, for example. You will learn this over time. So bila you sebut coming, for example, underdeveloped. So what are your potential root cause? Okay, so it could be resist too thick, or defect, or develop time too short, or develop a chemical too weak due to aging, or resist expired. So bila you relate back to the CED process, there could be 10 different places where could lead to this single problem. Okay, so that's why kadang-kadang you punya time tu will be spent on identifying the potential problems, then potential root causes. Okay, overdeveloped, underdeveloped, banyak lagi issue. So just let me finish all the common issues first. Resist addition. So for example, if you're supposed to get this, you're supposed to print like that. Supposed to, but what you're getting is this. Collapse. Macam bangunan terbalik. This called resist collapse or pattern collapse. We call it pattern collapse normally. So this is due to potential root cause addition. Maknanya you punya gum tak kuat lah. Bahasa mudah, gum tak kuat lah. It's actually due to addition. So then you have to narrow down to HMDS. Is it okay? Is it the flow rate is fine? Is the HMDS not yet expired? Is the vaporization process okay? Is the temperature of the plate okay? Is the duration fine? Is the placement of the wafer on the ADH plate is fine? Then you have to narrow down to ADH if it's due to ADH. If it's not due to ADH, it could be the spin speed too high during coating and during developing. You have to then move on to coating and developing. So you have to identify all the potential root causes before they can be presented next day, 8 a.m. Okay, so can you appreciate now what sort of works expected? I hope so. Right, print bias. So I'll go through a few more minutes. Print bias means the difference between your intended feature size from the mask and then your actual feature size on the resist. So we call that as bias. Bias ni sentiasa ada due to some issues. Okay, maknanya you're supposed to print say 100 nanometer, but there will always be 0.5 nanometer off on one side. Maknanya you're supposed to print 100, then kalau you print exactly the same, mungkin you always end up with 101.5. This is a 0.5 higher. Then that's called print bias. Okay. So the reason could be underexposure, overexposure, underdeveloped, overdeveloped, resist swelling. Okay. You want to print this big space, space, in this case, space, you end up like that all the time. You adjust dose pun dia akan sisa off sikit. Okay. So ataupun kalau you measure line, you want to get this, but you're always getting this all the time, always on the lower side. If you're measuring lines, you can pay attention. Is it space or line? Is it the lines or the holes? Okay. Interference is another issue due to reflection and incident light kat sini. You expose, and then at the same time, due to high reflection of the silicon wafer, normally reflect around 40%, there akan ada some reflection. Due to this, dia punya wave ni dia akan sinusoidal. So you're gonna have constructive and destructive interference in periodically. So as a result, you're gonna get standing wave. Okay, ini dia punya sinusoidal shape of the incident and the reflected light. So you're gonna get some regions overexposed, some other region underexposed. So maknanya resist U is supposed to print something like that. 3D, saya draw macam ni. So you're supposed to print something clean like this, but you end up having ridges. Ridges ni kalau you tengok dekat cross section from this side, you tengok mata kat sini, mata itu contoh. So you're gonna see sinusoidal punya wave. Exactly. Periods. Dia ada period. Macam typical sinusoidal wave. Tengok yang kena buat ni. Dia ada peak, dia ada trough, then you're gonna see the frequency, all those stuff. So it's due to standing wave issue. Okay. So you can see here the demonstration of standing wave problem. You can see you want to print exactly like that square, but you end up with like that. So this is optical issue dalam lithography. Optical issue due to interaction of incident light and reflected light. Incident light like that from the scanner, reflected light like that. Due to this interaction between this and this, you're gonna get destructive and constructive interference at different locations across the vertical patterns. Okay, so you can dapat ridges lah. So it's called standing wave problem. Okay, very clear, right? You can see very clear period. So peak and trough. So if you look at the cross section, you're gonna see something like that. So let's just stop here. Saya nanti kita stop for 10 minutes, then I'll come back to continue standing wave, and then a bit on LER. That is part of the assignment, and then we're gonna finish off with this part, and perhaps we can continue with etching a little bit before we stop our today's class. Right? Any questions so far?
No, Doctor.
Is it clear?
Yes.
Anyone with questions? Clear? So you have got some introduction to the troubleshooting punya framework lah, framework mindset. So it's more comprehensive than that actually. Tapi saya just summarize here. If you want to relate to what I said just now about the problem identification sampai preventive, so you can search for 8D report. Saya tulis ni. You baca ni, study ni is going to help you in your internship and your first job later on. 8D report. 8 disciplinary report. Discipline lah, discipline. 8 disciplinary report from D1 until D8. D1 apa, D2 apa, sampai D8. Kalau you boleh get all the information from D1 to D8, you can then close the problem or solve the problem in a very systematic way, structured way. Tak adalah macam try ni lah, and you waste your time. It's very structured. Framework dah ada lah. So that's engineering part of lithography. Right, so now 11:03, we'll meet again 11:15, okay? 11:15 lah, lebih kurang 12 minit lah. So I'll see you again then. Bye for now. Assalamualaikum. Okay, let's continue. Let me share again. Scars. Right, can you see the slides on the screen? Let's confirm. Right. Thank you very much. Let's continue. Standing wave. Okay, standing wave is not tolerable. So standing wave is considered bad. We don't want to have standing wave in our printed patterns. Okay, we want to have a very clear vertical edges on the patterns, not the wavy type. Okay, so it's bad. And this has to be eliminated. This issue has to be eliminated. So how to do that is, what we can do is we have to, if you go back to the sketch, silicon. So what you have is, you want to have this. It is intended. You're supposed to have that, but you actually have this issue, standing wave. Okay, SW effect, standing wave effect. So it's due to the interference between the incident light and the reflected light. And silicon reflects about 40% of the incident light. The question is, why silicon reflects about 40% of the incident light? Anyone? Anyone? Why silicon reflects about 40% of the incident light? Why so high? I want to ask Go and Kali, who work on this as your FYP. Okay, Go, come on. Why 40%, Go? Why is such a high reflection from silicon? Before we discuss about the solution, so why is it so? Why is it the case? Understanding the problem, defining the problem. Go. Why is it 40%? Wanna go? Right, okay, let me see. Silicon has a smooth surface, so kalau smooth, then why is it 40%? Why 40%? Why not 20%? Why not 10%? Why not 5%? Kali? Ni saya drill your FYP boleh eh? FYP could be potential question as well during your internship interview. Your thesis, huh? Right? Kali? Why not 10%? Why not 5%? Why not 15%? Why 40%? Anyone else? Other than Go or Kali? Faris? Faris, what do you think? Why 40%? Specular reflection, yes, specular reflection, but why 40%? Why not 10% of specular reflection? Or 20%? Or 25%? Faris? Anyone else? Okay, repeat the question. Okay. Why silicon has a very high reflection? In this case, about 40% of reflection. Kenapa silicon ada high reflection? Sekarang isunya standing wave. Due to reflection of the light, that results in formation of vertical ridges on the resist patterns. So now, before we discuss about the solution, why is it high reflection? Before we talk about the standing wave on the patterns. Anyone else? Recall from your 386. Optical punya part tu. Ya tak? Kenapa? Kenapa high reflection? Anyone can give me the equation If you still can recall, or the name of the equation that can relate the reflection to the 40% in this case. Anyone? Ingat tak equation tu? Okay, so I go say something now. High refractive index causes more reflection. Yes, high is due to its high refractive index. Okay, berapa go refractive index? Can you recall? Silicon is due to the difference in the refractive indices between air and silicon. Air punya refractive index berapa? And air. Go back to 386. Berapa? And silicon. Okay, I will say 1.0 and air. And silicon berapa, anyone? All right, about 3.5 to 4, more or less. Okay, actually, it'll be around 4, 3.9. It depends on the wavelength. It's wavelength dependent though. But then anyone can recall the equation starting with F equation, which governs this reflectance thing. Anyone? F equation. Lupa dah. Fresnel, right? Fresnel. F-R-E-S-N-E-L. Fresnel equation. Okay. R equals to, it goes back to the basics. So that's why when you talk about process, you have to go back to the physics. And silicon and air plus and silicon minus over plus squared. Then you're going to get about 35 to 40% of reflection. So this reflection causes problem to the resist because it results in the formation of standing wave on the vertical ridges. Okay, so kita nak standing wave. So to be able to do this, to eliminate this problem or to reduce this problem significantly, you need to introduce a very thin layer of bottom anti-reflective coating. Okay, so go dengan kali last time work on ARC, this part anti-reflective coating. This was tanya dia. Okay, so you have to introduce a layer, a very thin layer below the resist. So that means before you spin the resist on, you have to spin something on first, and this something is called bottom anti-reflective coating that can help suppress the reflection from the silicon surface. So when this reflection is suppressed, your standing wave is suppressed as well. So instead of getting these vertical ridges, you akan dapat a cleaner version of the pattern ataupun much lesser. You tak sedar lah, tak nampak. Okay, before the resist spinning, apply bulk layer first, typically about 100 nanometer or so. Spin coat juga. Dispense macam resist tapi is bulk instead of resist. Spin, bake, then go to the resist, spin, soft bake. Okay, so that's one way, bulk. The second way to solve this problem, standing wave, is by optimizing your PEB process. PEB bila? Which step is PEB? Where is PEB step? In the 8 steps. After which one? After which step? PEB? After E, right? After expose. Expose, then PEB, then develop, then hard bake, then VI. Okay. So optimizing PEB can help reduce standing wave. Photoresist glass temperature, TG, resist ada dia glass temperature. Baking temperature needs to be higher than TG in order to induce thermal movement of photoresist molecules. So bila you ada ridges kat sini, dia kasar kan? Dia macam actually resist molecule lah yang form the ridges tu due to the optical punya issue, okay, interference, destructive and constructive interference. So the moment you introduce heat to the resist after the exposure, even though the patterns are not yet developed, kita tak D lagi kan, baru E kan, belum ada pattern lagi. It's just latent image. It's just aerial image dalam resist. Yang dah ada due to the reaction during the exposure, the solid photosolubilization, hardening, blah, blah, blah. Tapi physical patterns are not there yet. So the moment you've got the ridges embedded lah, sebab tak nampak kan, embedded dalam resist tu, to be waiting to be displayed if you have the standing wave problem. So this thermal in PEB, thermal introduction, will induce thermal movement of photoresist, which will cause a rearrangement of the overexposed and underexposed photoresist molecules. So resist yang ada kat regions yang rough tu dia akan rearrange their position and dia akan smoothen the ridges. Okay, daripada tu dia akan jadi smoother sebab dia nak pergerakan. So they can help to smoothen the ridges. Okay, hence reducing or eliminating either one, depending on the optimum setting of the standing wave problem. So it will average out the standing wave effect on the ridges and will smooth the sidewall and improve resolution of the patterns later on. Okay, sidewall ni kita panggil vertical ridges ataupun sidewall sama. Wall lah tepi ni. This is the words that we use in litho. For DUV chemically amplified resist, PEB provide heat needed for acid diffusion. So essentially, if you talk about DUV resist, then there'll be acid diffusion because DUV resist uses PAG, photoactive acid generators. Photoactive acid generators. So this acid diffusion will help to smoothen the ridges. After the PEB process, the images of the exposed areas appear on the resist due to significant chemical change. So diffusion to chemical change now. Right, how do you do PEB? We've discussed last time briefly. Typically, the temperature is between 110 to 130 for about 1 minute. For the same kind of PR, PEB usually requires higher temperature than soft bake. Okay, we discussed last time. Soft bake is typically 90 to 100 degrees C. PEB is typically 110 to 130. And hard bake is usually higher than this, 130, 140, depending on the resist developer combination, of course. Okay, insufficient PEB will not completely eliminate the standing wave. Kalau you dah buat PEB, but then you still can see the standing wave, but a bit reduced. So that means your PEB is not optimized. Okay, overbaking on the other hand will cause polymerization and affect resist development. Instead, kalau you overbake dalam PEB, terlajak baking ke ataupun apa ni high temperature, then macam you bake cake lah, dia akan jadi keras dan selepas tu susah nak remove. Okay, bila you go for development stage, it will be harder to remove the intended areas. So you end up with CD punya problem juga lah. Okay, depending on line of hole, you akan overdevelop, underdeveloped thing will come back because PEB is not optimized. Padahal isu asal ialah standing wave elimination. But then you try to optimize the PEB wrongly, that will then cause the development to be affected. And your other problem comes, which is your CD underdeveloped or overdeveloped on top of a standing wave problem. Ataupun you might eliminate standing wave to some extent, but you introduce the ICD problem pula. Okay, so that's it. They are always interrelated to each other. Right, so let's see the simulation of diffusion during PEB. Okay, resist profile simulation in this case. So it's related to diffusion length in this case, but it's not the diffusion length yang kita discuss dalam 386 because that one is like generation to recombination punya distance gone through by the carriers. But in this case is how far does the molecules diffuse during the PEB process due to the thermal effect by the PEB. They diffuse and smoothen the ridges. Okay, so if you put your acid diffusion to 20 nanometer of diffusion, then you'll still get the ridges. You can see the ridges here. But if the diffusion of the molecules is longer, maksudnya dia ada lebih pergerakan, then you will see smoother wall, side wall, and 60 you have smoothest one. If you compare 20, 40, 60, just to illustrate. Okay, so it's due to diffusion of the photoactive acid generators for DUV resist in particular. Kalau tak generally, then molecule resist lah punya movement. Right. Another problem is PEB delay time. So bila you optimize PEB, say if you want to extend the time, you will also introduce another problem that's called T-top formation. T-top, PEB delay time dia akan induce another problem called T-top. What is this T-top? Top formation means it's supposed to print like that, but you're getting T-shape. Hammer-like lah, hammer macam hammer. Kepala ada kiri kanan. So this called T, so the T-shape lah. T-top, so and it happens on the top of the features, and we call that T-top formation. Okay, due to PEB delay time, so it will affect the resist quality in this time. For example, if you don't have any delay, 0 minute, so this is what you will get. So the resist is quite good, but then it's a bit positive. Dia kembang lah kat bawah, it's a bit positive. Kalau negatif macam tu lah. So saya explain itu. So if you delay the PEB on purpose, for example, katakanlah ada problem ke PEB wafer left in the PEB module extra by 30 minutes, then you will see T-top develops. Okay, so you get that, and then you believe you develop, you're going to put T-top. So this is what you intend to get, and this is what you actually get. So due to reactions with airborne molecules such as ammonia or amines that will neutralize acid near the top of the resist, forming a mushroom cap. Macam mushroom lah, ataupun hammer-like, ataupun T-top, right? Reaction with certain substances such as thionite neutralize acid near the bottom of the resist, forming a foot. It can also be like that. So that's why when you go into litho punya department, yellow room tu, you have to control the amount of ammonia in ppm. I think ppm, if I'm not mistaken. So dia kena below certain levels of spec. Maknanya kita control juga spec and QA control environment has to be with certain temperature, certain humidity, with certain level of ammonia, certain level of blah blah blah. So ammonia is one of the main parameters that is under control because you don't want to induce T-top formation dalam fab though. So kalau just imagine if your ammonia is exceeding certain level, walaupun tak bahaya to human exposure, human interaction, tapi it already interacts with the resist, and that causes the T-top issue. Okay, T-top issue. That's good. Okay, so that's another issue. Okay, resist profile that you can also get. Okay, you perhaps can relate this to LER, line edge roughness in assignment. I'm not sure if you've done this, so it's about time to pick this up if you want to. Okay, resist, you normally have, ideally kita nak print a very square shape, but most of the time you'll get a bit positive, a bit trapezium lah, if you like, a bit trapezium, positive sikit. This is still considered okay. Kalau dia terlalu wide at the bottom, then not okay, right? Nanti bila algorithm dekat SEM dia takkan dapat identify the correct CD. Okay, bila dia measure dekat top, measure dekat middle, bila dia measure dekat bottom, then bila dia nak conclude the final CD tu dia pening sikit sebab dia detect so big difference. Okay, LER is an issue where you can see roughness on the lines that are printed. Kalau you tengok top view, this line, you're supposed to get like that. Top view, atas wafer, dari atas wafer. If you have LER, you're going to have some roughness. Ini bukan cross section regions dia, ni dari atas top view. Top view, you're going to see some roughness on the edge. Okay, so just like that. So this is the issue. So sekarang ni the question is, how do you reduce this variation? It won't be a big deal if you are printing a big CD, for example, 300, 400 nanometer. You can still tolerate the roughness on the edge because on the side of the profile, because if you're printing 200 and your roughness is like very small, so the noise, signal to noise, and noise is the roughness, is very, very small in comparison to the right, to the intended signal, which is the CD target, 200, 300. But just imagine if you have the very same roughness on a very small CD, 10 nanometer, 20 nanometer, and your magnitude of the roughness is still single digit nanometer over 20 nanometer of CD target. So that means your noise is already very high in comparison to your CD target. Berbanding, say if your noise is like 5 nanometer of roughness, but your intended CD is like 300, so 5 over 300 is quite nothing, right? Ataupun kalau you nak guna signal to noise ratio, then 300 over 5 is, you can suppress the noise lah. Okay. On the other hand, if your intended CD is like 10 and then your roughness is 5, and that's like half of the intended CD, so that can interfere. Okay, interfere. So that means when you measure here, the algorithm is looking for 10, but it's finding 5 as well on the side. So they're complaining. So that's why at that particular point, when you go for state of the art punya chip yang high end punya, yang 7 nanometer, 5 nanometer, you cannot tolerate the very same magnitude of the roughness on the edge. Okay, so how to solve this LER issue? I'll leave it to you. Okay. In future trends, when I talk about future trend, it's referring to NGL, next generation lithography, but we've discussed a little bit on EUV, which represents the current trend. So NGL including EUV, smaller feature size, higher resolution features, reducing wavelength, PSM, and other optical technique you want to do, or you want to incorporate in order to make sure that your printed patterns are good. Okay. So we need up to 2014, yeah, it's quite old. Feature size, say you can see the feature size from down to 0.1 something or 0.07. Sekarang dah about TSMC is talking about 3 nanometer, 2 nanometer using EUV. Okay, so this is the next generation lithography that we talked last time is actually the current lithography system that is available. Sampailah kita push the Moore's law to the very end, okay, to the size of the silicon atoms. But even before that sampai ke size of silicon atom pun, it's already super challenging to get the optics to be right in EUV. At this point, where you can see the complexity of the system and the printing is like down to 5 or 3 nanometer, and the optic is already like costing the system to be 300 million USD already. Okay, just to print 5 or 3 nanometer. So kita tak discuss tentang the limitation of silicon atom yet. Baru optic to get to the 5, optic to get to the 3. So that means nak sampai ke dinding tu, nak push Moore's law to the very end, down to atomic size, as silicon atom size, the optic is already suffering, and you still have to figure out all the R equals K lambda over NA and the DOF equations, and you have to increase the numerical aperture of the lens in the EUV system to go for high NA. Okay, so if you recall back the features kita discuss itu kan, R equals K lambda over NA, and we have discussed how to reduce the resolution or to print smaller size, which is resolution, right? So you can do that by reducing the numerator product ataupun increasing denominator, right? Barulah kita boleh reduce R. So that means reducing the process factors K and reducing the wavelength, which is already at the limit as of now, EUV 13.5 nanometer as the illumination wavelength, or increasing the NA, increasing the numerical aperture of the system. So if you want to push for higher, so this will become super crucial, increasing the lens punya NA and numerical aperture. You can check EUV punya current NA berapa, and how do you measure NA, and why NA, how do you optimize NA to higher level? What is required in terms of the lens design and aperture, and material quality and the size and the focus and the DOF effect. So dia banyak it's just a simple equation can affect so many things in the future. Okay, before you get to push the Moore's law to the very end. Right, PSM is another thing. How many pages do I have? Okay, let me just fly through this. We discussed briefly last time. There are many techniques that you can use in order to ensure good resolution, good aerial image of the features especially if you are printing very small lines or very small technology nodes. Okay, so dia ada banyak lagi method yang ada. So among the methods available is called PSM, phase shift mask. Kita pakai dalam lithography ya. Maksudnya during the printing process kita pakai PSM instead of a normal reticle. Dan banyak lagi ya, you can check on OPC, optical proximity correction, you can check on RET, reticle enhancement technique dalam lithography. These are all advanced stuff in order to get the features to be superb at low sizes. Okay, for example, if you use normal mask on the left, okay, if your features are very closely separated, maknanya terlalu dekat ya, kita discuss tentang we cannot afford to resolve the pattern, right? Because it's too close. The pitching is too small. The pitch is too small. So in this case, if the light coming through and the chrome and the glass punya distance is too small, then at some point, if it's too close, then you have constructive interference in between. So that means bila kita expose, the features cannot be resolved by the light because dia terlalu dekat. Okay, so bila you print, bila ada constructive interference, then you will get to see resist coming because exposure is not enough. So photo solubilization or the hardening effect will not be properly in place. Okay, bila you buat exposure tu. Right. So as a result, okay, let's see. Then the design pattern, okay, if your design pattern is something like this on the reticle, maksudnya you nak dapat macam ni lah. You're supposed to print this. You're supposed to print this. You're supposed to print this as well. But when you develop, you end up with final pattern. This you get this, but you miss the one in the center. Okay, because the features cannot be resolved because they are just too small. If you use a normal mask, especially if you're talking about low technology nodes. Okay, try to check bila kita start pakai PSM. At which level? Is it below 100 nanometer? Is it below 200? Is it below 50? Is it below 22 nanometer? Okay, try to check. Bila kita exactly pakai PSM. So with PSM, dia ada coating ya, facial coating. So di PSM punya reticle. They both are reticle, cuma satu normal, satu PSM. So there'll be different mechanism at play during the exposure process. So dia punya interference will be different and light intensity will be different. You're supposed to print features like this. You're supposed to print this, supposed to print this, supposed to print this. And your final pattern will be following your intended reticle design. With PSM. Without PSM, dia akan hilang kat tengah. Sebab dia tak nampak lah. Sebab dia tak boleh resolve kalau ada constructive interference. With the PSM, the constructive interference in between is resolved, is soft, no longer there. Therefore, you can print the features as intended. Okay, that's the effect of PSM. Right, NGL, EUV, X-ray, massless litho, E-beam or ion beam, immersion litho. We have range of different lithography options before we get to EUV. Sebelum ni ada immersion lithography. Okay, immersion lithography, so we're going to go through shortly. So EUV 10 to 40 nanometer currently is using 13.5. You can see the video I've uploaded on ELAN on EUV system. Tengok the complexity, shorter flank and reduce NA. Well, if you talk about the current EUV, then we are trying to increase NA. Try to read what is the typical range of NA. Mirror basis due to strong absorption and short wavelength. Dia tak boleh pakai typical lens lah, because lens ada dia punya own parasitic absorption at low wavelength. So they can absorb light, then the light will not be passing through the lenses. Then there won't be any proper lithography. So they're going to pakai mirror in order to avoid parasitic absorption in the lens. Okay. So EUV system, you can have a look later on. Saya pun dah uploaded few videos. X-ray lithography, super expensive. It doesn't make it into line. It's not used, unlikely ya, tak guna. X-ray litho punya mechanisms different. And then still on X-ray, this is EBL, E-beam lithography, use electron beam to do the lithography. We have one unit in NOLAB. Okay, here it is very good to print small features, but then the speed is very, very low. So low throughput. So when you talk about mass production, if the throughput is very low, it won't be commercially viable. Throughput wafer per hour that can run through the system. Number of wafers per hour, we call that as throughput. So if your system has a very low throughput, it won't make it into mass production because it's just not feasible. It's not commercially viable. Kalau untuk lab boleh lah, untuk EBL ni. But then for mass production, EBL will not work ever. So that's why EUV is in place. EBL punya system, EBL exposure system, IBL also doesn't work. We have another system called immersion lithography. So that means the whole projection optics. Dia ada dekat bawah tu, you can see here. This the projection system. In between the projection system and the wafer, you have water in between. Okay. Ada air, sebelum ni kita ada proximity kan. So projection system dengan wafer ada some small distance, but that small distance is made out of what? Kalau kita ada small system, small proximity tu, small distance, what is the material in between? Sebelum ni. What do you think is the material? I leave that to you. Okay. Cuba search lah. Kenapa kita kena pakai okay, search lah. Kenapa kita kena pakai water here? Why using water between the projection system and the wafer? In this case, we call it immersion lithography. Maksudnya lithography dalam air lah. Kita guna air untuk buat the optical punya process. See, projection lens here, then purified water is used in between the wafer duduk bawah ni. Dan you punya resist kat bawah ni lah. So in between ada DI water lah. DIW, DI water. Why immersion lithography? Okay. It's not for cooling because it's not hot. It's for optics. Reflection purpose? To some extent, yes. Cuba cari kenapa kena pakai immersion lithography. What is the motivation of immersion lithography? What is it trying to solve? What is the current problem if immersion is not used? What are the features? What kind of features expected without immersion if you're running before immersion with system? Okay, it's gonna be interesting. Yeah, it is a medium, but why? What is the technical features of the DI water that makes it suitable to be incorporated into immersion lithography system? Okay. Immersion system, saya kalau saya jumpa saya bagi some notes to you. Okay, try to understand what is the basis. Then kenapa EUV sekarang dia tak pakai immersion? If immersion try to solve some problem dekat previous system, then why EUV doesn't use any immersion? What makes it different than previous system? Ataupun dia dah completely change the whole atmosphere in the chamber so that you don't really need the eye water to be used as the interface. Okay. So try to compare, try to understand that, right? Yes, done. So we're done with lithography and we are going to, today's what, Friday, right? Friday, okay, for next week. So I'll see you next week, Monday, 1 to 2 p.m. To continue with etching, right? So any questions so far? Ada soalan? Tak ada? Ada. So is it okay so far? right? Ada? So you're clear on lithography so far? Ada soalan macam tadi boleh jawab ah. DOF issue ke, CD issue, defects, immersion. Yeah, good. So let's recap. Today assignment 1 is due on Elan. Then next week, right? I told you about the test. Saya dah beritahu itu kan last week kan? Oh, this week, was it this week? Earlier this week, right? Will be test, right? Test on Friday, 2 hours. Yeah, next Friday, 2 hours. Did I tell you last time? I think I told you a few days back. It's okay. So 2 hours test open book from topic number 1 up to lithography. Okay. Sama konsep macam ZAT punya test. So 3 questions, 2 hours. Right, anything? Okay, all good. Right, then I'll see you Monday, inshallah. Bye-bye. Take care. Assalamualaikum. Welcome.